Pythagoras' theorem is based on the idea that the sum of these two sides, each squared, is equal to the square of this side. The tricky part, I think, sometimes is remembering which letter is which, but in truth, what really matters is that the long side is the sum of the two shorter sides, squared, of course. So just think about it in terms of the long side and the two short ones. And it's quite obvious in a sense because the long one is made up of the two little ones. It can't be that one of the little ones is made up of the long one. So this is why they write it as C equals A plus B, and of course all squared. They have to be squared, it doesn't work otherwise. All right, so what they're suggesting is if there was a big square coming off of here, the area of that big square would be the same as this square here plus this square here. So if you were to draw those three squares, the area of this one, the area of this one is equal to the area of that one. So how it kind of gets tricky in a sense, it's fairly straightforward, isn't it? If they sort of do the two sides as maybe, so maybe this short side here could be 2. This slightly longer side could be 3. Okay, so then we get 2 squared plus 3 squared. So 2 2s are 4, 3 3s are 9, and we get 4 plus 9 is 13. And then we have to find, to be able to work out what C is, the square root of 13, which of course is not as easy as I just suggested. So that would be the square root of 13. The square root of 13. Okay. So we try some different numbers, see if we can make it a bit easier. That will obviously require you to use a calculator. So perhaps they were 3 and 4. See if that works a bit easier for us. And we might not need a calculator this time. So 3 3s are 9. 4 4s are 16. And so we get 9 plus 16, which is 25. And of course, then what we need for our C is the square root of 25. That one I can do in my head. So that's a 5. Okay, so if you're lucky, you're told what these two sides are, and then you can work out what the final side is. If you're not so lucky, of course, what would happen simply is that you're going to have something perhaps like this, same sort of triangle, and perhaps what it will be, and I'm going to use the same numbers again because we know what the answer is that time. It might be that you've got a 5 and a 4, and then you're trying to find out what this one is. Okay, so in that case, we label them A, B, and C. We know the long one this time is one of the short ones that's missing, so we kind of write that down. We're going to have A plus B equals C. Of course, they're all squared. And then we're going to have A squared plus 4 squared equals 5 squared. So then we have A squared plus 4 4s, 16. 5 5s, 25. Nearly there. And you just need to do a bit of your algebra then to rearrange these. So we take away 16 from both sides. So minus 16 from there gives us A squared and nothing. And then minus 16 from there will give us 9. So we've got A squared equals 9. So A equals the square root of 9. So A equals 3. So effectively, the only other way you would do this is if we had the A but we didn't have the B. But of course, the procedure is exactly the same. So if we just have one of the shorter sides missing, it's a matter of working it out and just rearranging it at the end, taking it off. If we have the long side missing, it's simply just this one squared plus this one squared will give us that one, and we just have to find the square root. I hope that helps.